Good morning. Today I am teaching the concept of theory of computation or flat. Theory of computation or flat subject. Now coming to the basic definitions of automata. What is an automata means? Automata simply a machine. Simply it is a machine. So what it will do means automata it represents the mathematical representation of computing devices. Means computing devices are nothing but simply it may be a desktop or it may be a laptop or it may be a calculator, like this. So internally, if you give some operation like addition, subtraction or multiplication, whatever it may be, so what internally will be happen? That will be how to represent in mathematical way. So automated definition is mathematical representation of computing devices and its capabilities. Simple definition. Now coming to the second one, what is formal languages means? Formal languages is nothing but some collection of strings. Strings. So what is a string means? We know that string is some collection of characters. We know that one. What is a string means? Some collection of characters. So what is a characters means? It may be a small a to small z, capital A to capital Z, or some numbers from 0 to 9, or some special symbols like this dollar or question mark, whatever it may be. Like these collection of these characters are simply called as a string, and collection of these strings are simply called as what? Formal languages. Now, these collection of strings, meaning is does not important. Meaning is does not important, but order is important. Meaning is that, for example, if you take AA, BB, AAA, so like this, if you take, they does not have any special meaning for this one, but order is important. Means after A's how many B's come, after B's how many C's come, like this. Order is important, but they does not have any meaning. But after 3 A's, 3 B's come, after 3 B's, 3 C's come, like this. Order is important. Like this, collection of strings is called as what? Formal languages. Now coming to types, how many types are there means nearly there are 4 types are there. Type 3 language, type 2 language, type 1 language, and type 0 language. Now coming to what is type 3 language means, Mark. Type 3 language is nothing but it is also called as a regular language or regular language, and this type 3 language is accepted by one automata called as finite automata. And what is type 2 language is? Type 2 language is called as context free language, CFL. Type 2 language is also called as what? Context free language. And this type 2 language is accepted by one automata called as push down automata, PDA, push down automata. And type 1 language is also called as context sensitive language. And this context sensitive language is accepted by one automata name called linear bounded automata. And the last language is type 0. It is also called as recursive enumerable language or REL. Recursive enumerable language, and this type 0 language is accepted by Turing machine. Diagrammatically, we can represent type 3 language is also called as regular language, and it is accepted by one machine called as finite automata. And this type 3 language is subset of type 2. Type 2 language is also called as context free language, and it is accepted as push down automata. And this type 3 and type 2 languages are subset of type 1. Type 3, type 2 languages are subset of type 1 language. And this type 1 language is also called as context sensitive language, and it is accepted by an automata called linear bounded automata. And type 0 language is also called as regular recursive enumerable language, and it is accepted by Turing machine. So the concept is clear that type 3 language is subset of type 2, and type 2 language is subset of type 1 language, and type 1 language is subset of type 0 language. So this is the concept regarding formal languages, the concept. How many formal languages I told that? I told that 4 types of formal languages are there: type 3, type 2, type 1, and type 0. And the relation between them is like this. Type 3 language is subset of type 2, and type 2 language is subset of type 1, and type 1 language is subset of type 0. I already told that type 3 language is also called as regular language, which is accepted by finite automata. And type 2 language is also called as context free language, which is accepted by push down automata. And type 1 language is also called as context sensitive language, accepted by linear bounded automata. And the last one, type 0 language, is also called as recursive enumerable language, accepted by two remission. Now, question is, why these 4 types of automators are required? Why we need 4 types of automators means, the question is, before going to that, why these many types of automators are required? Simple definition is there. What is an expressive power of an automata? What is an expressive power means? Simply it is the number of languages. The number of languages accepted by an automata is simply called as what? Expressive power of an automata. So, what is an expressive power of an automata means? How many languages it will accept? For example, if you take finite automata, how many languages it will accept means now only one. If you're coming to push down automata, it will accept two types of languages. Now, coming to linear bounded automata, it will accept 3 languages. Coming to Turing machine, it will accept 4 languages. Now, before I gave the question that why these many automators are required means, before going to that one, finite automata coming, if you take one example, L1 language L1 is equal to a power n greater than or equal to 1 means it is meaning that n should be minimum 1, thereafter 2 or 3, or like this you can take. Minimum should be 1, after that it may be 2 or 3 or 4 like this. Now, if you take n is equal to 1, what is the language L1 means? Single A. If you take n is equal to 2, it will A. If n is equal to 3, what it will be? 3A's. Like this, if you take n is equal to 4, how many A's will come? 4 A's will come. Like this, if n is equal to 5, how many A's will come? 5 A's. Like this, so on, n number of A's will come. Now, the question is, can we construct finite automata for this one means? Yes, we can construct a finite automata for this one, because like this, from starting state, say S1, final state S2, we need a minimum single A, means here n is equal to 1. So, if you have to take minimum 1 A means, so if you take single A, then it will be satisfied and it will go to the final state. So, minimum single A is okay for us, and if you take single A, we will reach final state. So, single A is okay. Now, after 1A, it may be 2 number of A's, 3 number of A's, 4 number of A's, infinite number of A's will come. So, infinitely means there may be a loop like this, and if you write like this in the loop, means infinite number of A's. So, starting state S1, final state S2, single A is accepted. After that A, any number of A's will come. So, here we are constructing finite automata. So, finite automata is construction is possible. And here in this diagram, no memory space is required, no stack is required, because for single A it is accepting after any number of A's it will go into the final state. No memory space is required, no stack is required. So simply finite automata does not take any memory space. Any memory space is not required for the finite automata. Now coming to second example, L2 language is equal to a power n, b power n is greater than or equal to 1. This meaning is that if you take n is equal to 1, 1a, 1b will come. If you take n is equal to 2, 2a's, 2b's will come. If you take n is equal to 3, 3a's, 3b's will come. If you take n is equal to 4, 4a's, 4b's will come. Means equal number of a's and equal number of b's, and equal number of a's are followed by equal number of b's like this. First First equal number of A's will come, then equal number of B's will come. Now the question is, can we construct finite automata for this language? Means we can't construct finite automata for this language. It's not possible. So for this type of languages, we have to take one memory space. That name is stack. So if you take stack, then construction for this language is possible. Like this. For example, for this language L2, a power n, b power n, where n greater than or equal to 1. If you take n is equal to 3, n equal to 3 means 3s and followed by 3 b's. So can we construct automata for this language? Means yes, we can construct like this. First, push these 3 a's in one stack. So we know that what is a stack means. Simply stack is a data structure which is following last in first out order or first in last out order. Stack simply like this. One side is closed, one side is open. One side is closed like this, one side is open like this, which follows last in first out order or first in last out order. Now, first push these A's into the stack. So A is pushed. Now, the next step is for every B, pop A. And for every B, pop A. For every coming B, pop A. Now, after pop all these A's, the stack will remain empty. So when stack will remain empty means, that meaning is that the construction of the automata for this language L2 is A power n, B power n, n greater than 1 is successful. So here one memory space is required. That memory space name called what? Stack is required. So now here we are taking, for the finite automata, we are taking extra one stack is required. So what is push down automata means? For finite automata, if you add one stack for this one, that is called as what? Push down automata. So like this, for equal number of A's, for equal number of B's, whenever A's come, we are popping the A's and emptying the stack is called as what? Simply a push down automata construction is possible here. So here we are successful constructing push down automata for type 2 language, like this language. Now question is, if you give one question is like that, L is equal to A power n, B power n, and C power n. This meaning is that if you take n is equal to 3, means 3 A's, after that 3 B's, after that 3 C's. So for example, if you take only one stack, first you have to push 3 A's like this, 1 A, second A, and third A, like this you have to push into the stack. Then when B's come, you have to pop A's like this. Okay, now when B's come, you have to pop A's means then A's and B's are removed. Okay, then C's are left. C equal number C's are left in the outside. So what is our target means? Entire for a given entire string, we have to empty the stack. But here, for equal number of A's, equal number of B's are popped. Okay for us, and C's are left. So for this type of languages, PDA construction is not possible. Why means for equal number of A's, equal number of B's are popped. Okay for us, but remaining C's are left. So now the question is here, PDA fails. PDA fails to construct an automata. So PDA fails to recognize where more than one memory space is here required. Where more than one memory space we have to require here. Now coming to same language L3, where L3 language where I gave that A power n, B power n, C power n, where n is greater than or equal to 1. I gave the condition. For example, if you take n is equal to 3, means 3 number of A's, 3 number of B's, and 3 number of C's. So for this language, push down automata construction is not possible. I already told you. Now, for this language, how Turing machine construction is possible, I have showing here. Now, so before going to construction, you have to take two stacks, stack 1 and stack 2. Now, so for 3 A's and 3 B's and for 3 C's, first push A's into the two stacks. Means for single A, you have to push into the stack 1. For single A, you have to push into the stack 2. So like this, for single A, we are pushing in 2 stacks. And another A, we are pushing into the 2 stacks. And third A, we are pushing into the 2 stacks. So each stack contains 3 A's and each stack contains like this 3 A's. Stack 1 contains 3 A's, stack 2 contains 3 A's. Now, when B's come, when single B's come, then pop 1A. And another B come, then pop A. And another B come, pop A. So like this, stack 1 is empty. Like this, stack 1 becomes empty. Now coming to stack 2. For single A, when C come, one pop A. When second C come, then pop another A. When third C come, pop another A. Like this, stack 2 also becomes empty. When both two stacks are empty, nothing but here we are constructing Turing machine is possible here. So Turing machine is possible, construction possible here when we need two stacks. So simply we can say that Turing machine is nothing but finite automata plus two stacks plus two stacks. Like this, we can say that Turing machine is nothing but finite automata plus two stacks are required. Or in another manner, you can say that Turing machine is PDA plus one single stack. Nothing but already we know that what is PDA means push down automata plus one stack. Already I told that. So PDA plus one stack is also true. Or Turing machine you can say that finite automata with two stacks. Like this, Turing machine construction is possible by using how many stacks means two stacks. Now, if anything is accepted by other automators, if any language is accepted by other automators, Turing machine is also accepting those type of language. For example, in the before example, I gave L1 language where n is greater than or equal to 1. I gave this language. This is accepted by I told that finite automata. So this type of language is accepted by finite automata means this language is also accepted by the Turing machine also. So those languages which is accepted by the other automators, those type of languages are also accepted by the Turing machine also. But reverse is not true. Those languages which is accepted by the other automators are also accepted by the Turing machine, but reverse is not true. Means the language which is accepted by the Turing machine, these languages may or may not accepted by the other automators. That's I gave like this. If any language is accepted by the other automators, Turing machine is also accepting those type of language. In the reverse case, if any language is accepted by the Turing machine, other automators may accept or may not accept. Reverse is not true. Now, among the four automators, which is more powerful means the more powerful automata is Turing machine. So, Turing machine is more powerful than finite automata, push-down automata, and linear bounded automators. Among all four automators, which is more powerful means Turing machine is powerful. Why means Turing machine is accepting all the languages which are accepted by the finite automata and push-down automata and linear bounded automata. So that is why Turing machine is more powerful. Now the question is, which of the following statement is false? I gave four statements. Finite automata plus one stack is more powerful than finite automata plus zero stack. Finite automata plus two stacks is more powerful than finite automata with one stack. Finite automata with three stacks is more powerful than finite automata with two stacks. Now we already know that finite automata plus one stack means simply push down automata. I already told you. Finite automata with one stack means push down automata. So push down automata is always powerful than finite automata. Push down automata is always powerful than finite automata. Coming to so this is true. This is true. Coming to next case, finite automata with two stacks is more powerful than finite automata with one stack. Finite automata with two stacks is nothing but simply I told that Turing machine. I already told this. Finite automata with two stacks is nothing but what? Turing machine. And finite automata with one stack is nothing but push down automata. So this is also true. Turing machine is always powerful than push down automata. So second is also true. Now coming to third case, finite automata with three stacks is more powerful than two stacks is this one is false. Why means finite automator 3 stacks is nothing but simply finite automator with 2 stacks only. 2 stacks only. So finite automator with the 3 stacks is nothing but Turing machine. Which is more powerful than Turing machine is false condition. Like this, which is false means third condition is false. Thank you.